Hello, in this video, thermal convection velocity sensor, which is one of the blood flow measurement techniques, will be discussed. I would like to start with showing what the blood flow measurement techniques are. As seen in the figure, there are lots of methods are available and these can be examined as non-invasive and invasive ones. But in this video, we are going to focus on the thermal convection flow meter. Let's examine these sensors in more detail. The working principle of the thermal control flow meter is based on the theory of conductive and convective heat transfer. Two sensors are supported either using inline flow bodies or insertion-style probes of the meter. These sensors are then interfaced with the fluid being measured. Heat is introduced into the flow stream of the fluid. A large amount of heat is lost with the increase in the flow of the fluid, and the amount of heat dissipation is measured by using one or both of these temperature sensors. An integrated circuit heats up one of the sensors, and it functions as a flow sensor, while the other sensor acts as the reference detector and finds out the fluid temperature. A continuous overheat is maintained by the circuit between the flow and the reference sensor. As fluid flows via the heated sensor, flowing fluid molecules transfer heat away from the sensor. This results in the cooling of the sensor and there is a considerable loss in energy. The thermistor T1 is heated to a temperature difference delta T above blood temperature by the power W dissipated by current passing through T1. These quantities are related to blood velocity U by where A and B are constant. The thermal velocity probes are shown here. By using these probes, the rate of heat removal from the tissue under probe is measured. RU is the velocity sensitive thermistor and RT is the temperature compensating thermistor. Catheter probes are designed with two types of sensors. The first type uses the thermistor shown in figure A, is cooled equally for both direction of velocity and the output of the instrument is a full wave rectifier replica of the true velocity. To overcome this limitation, two additional thermistors are located downstream and upstream from RUs as shown in figure B. Depending on the direction of velocity, one or the other is heated by the heat carried through the blood from the thermistor RU. These two additional thermistors are placed in a bridge that is balanced for zero velocity. A comparator detects the bridge unbalanced and switches the output from positive to negative. Also, like shown in figure C, probe uses two velocity sensors arranged so that one is exposed and the other is shielded from the fluid velocity. To correct measuring velocity profiles, probes can be placed at the end of hypodermic needle and inserted perpendicular to the vessel. As shown in figure 2.20, inside of the thermal convection probe, there are two concentric rings and a central disk. The concentric rings are isolated thermally and electrically from each other. The central disk is heated 1 or 2 Celsius degree over the temperature of tissue by using constant power supply. And the temperature difference of 2 or 3 Celsius degree is established between the disk. The constant temperature sensor circuit is shown here. The circuit is initially unbalanced by adjusting R1. The unbalance is amplified by the high gain op-amp and output is feedback to the power the resistance bridge. I can summarize the operation of the circuit in that way. Assume that thermistor RU is 5 degrees higher than the blood temperature because of self-heating. If the velocity increases, RU cools and its resistance increases. A more positive voltage enters the non-inverting op-amp terminal, so velocity of B increases. This increases bridge power and RU heats up, thus contracting the original cooling. RT provides temperature compensation, and the system uses high-gain negative feedback to keep the bridge always in balance. Also, the linearizer is used for improving the nonlinear behavior of amplifiers to increase efficiency and maximum output power. The references used in this video is shown here. Thank you for listening to me.